This conference will now be recorded.
Very good morning, students. So today we'll be taking up few numerical problems from ray optics chapter. So far what we have discussed, I'll take up questions from this particular portions, the portion of the lens. Okay, so far, like till now, we have to learn prism, refraction prism, then microscope, telescope. These are remaining. This will do subsequently. So today, let us take few numerical problems which are being asked in JEE main exams in the previous years. That will give you some idea about how questions come and how to prepare. Okay, so let us read this problem. This problem says the size of the image of an object which is at infinity. So the size of the image of an object which is at infinity is formed by a convex lens of focal length 30 centimeter is 2 centimeters. So size is given, size of the image. You know the size of the image. If you know the magnification, there you can use that. Okay, so here this is 2 centimeter given. This is object size. Okay, if the concave lens of focal length 20 centimeter is placed between the convex lens and the image at a distance 25 centimeter from the convex lens, calculate the new size. You have to find out the new size of the image. I'll explain the situation from this figure. Look first what is said. An object is placed at infinity. Okay, so u is infinity in the beginning for this convex lens, and it forms an image whose image size is 2 centimeter, and the focal length of the lens is given as 30 centimeter. So you know eventually the image will form. Okay, image will be formed by this convex lens at 30 centimeter itself, because the rays are parallel. They will, so the image, see, you look here now, a concave lens of focal length 26 centimeter, sorry, 20 centimeter focal length. See, it has focal length 20 centimeter minus 20 centimeter. Okay, it is placed actually in between the image formed by the convex lens, that is I1, say I1, and the convex lens, and from convex lens it is 26 centimeter away from the convex lens. Okay, so this is what is depicting in the figure. Now you have to find out what is the size of the final image or new image. Look here, actually, as I said, you will see there will be image formed by this convex lens which is at I1, say, and this I1 will actually act as virtual object for this particular, or it will act as an object for this concave lens. Okay, concave lens. and then finally the image will be formed at I2. So you need to find out the image size, final image size. In fact, you know the position of the image from the convex lens, that is 30 centimeter. Now this concave lens is at 26 centimeter, as you see in the figure. So what is the object distance for concave lens? So object distance will be this much, which is 4 centimeter. Okay, so for the object, now for the concave lens, the object is at 4 centimeter and it is actually positive 4 centimeter, and focal length is 20 centimeter, as you know. So now we have to find out where is the image form, where is the image forming. Okay, so 1 by v minus 1 by u will be equal to 1 by f. So you know 1 by v we have to find out minus of, see u is actually positive, so 1 by 4, this is minus 1 by 20 focal length. Now 1 by v is equal to 1 over 4 minus 1 over 20. This will be actually 5 minus 1 over 20, which is giving you v is equal to 5 centimeter. So once you know the image distance now, so you have got this is 5 centimeter alone. You have to find out the image size, right? So we know image size, this is actually image h prime is equal to v by u. So v by u into h prime. So where is v by u? V is 5, u is how much? 4 into h prime. H prime is 2 centimeter. So this is 5 by 2 and it is 2.5 centimeter. Okay, 2.5 centimeter. So this is actually the answer. You can see and choose from here. This is the one. Okay, so let us go to the next problem. So this was from 2023 main paper, 2003. Now we'll solve this problem. A double concave lens, a hollow double concave lens is made of very thin transparent material. Thin transparent material, it can be filled with air or ether, of two liquids L1 and L2 having indices mu1 and mu2 respectively. The lanes will diverge a parallel beam of light if it is filled with. If it is filled with air and placed in air, and immersed in liquid 1 L1 and L1 immersed in L2, etc. You can see mu2 is greater than mu1 and that is greater than 1. Okay, so here you have to find out the lens will diverge a parallel beam of light if it is filled with. That means when the lens will act as a concave lens. Let us try to understand from the lens maker's formula. Okay, that will give us a very clear understanding from here. So we have to solve it from lens maker's formula. Yes. So lens maker's formula, what we know? We know 1 over f is equal to mu2 minus mu1 divided by mu1 into 1 over r1 minus 1 over r2. So this is what we know in case of lens maker's formula. Actually, you know what? Here the focal length, as I was discussing yesterday, the focal length is actually related to the refractive index of the material created, like material with which the lens is being made, and refractive index of the mu1 is the refractive index of the medium, and r1 and r2 are the radii of curvature. So here mu2 is the refractive index of the material and mu1 is the refractive index of the surrounding medium. That we have already understood. Lens made of the material. Lens, refractive index of the lens, material of the lens. So for a double concave lens, that means this one. So in this case, you know, this R1 is this way, R2 is this way. I think this is refractive indices. So radius of curvature for R1 is actually, see, R1 will be negative and R2 will be positive eventually here. Now, since R2 is positive, this is negative and this is negative. So this quantity will be ultimately negative quantity. Okay, so 1 by R1 minus 1 by R2 will be, this quantity will be negative at least. So this part is negative, okay? This part is negative. Okay, now let us erase this part and see. Okay, so what we are going to discuss is that since this is negative, the focal length or focus of the since it is negative, it will act as actually overall it will act as negative focal length. So since it is negative, this will be also negative. The focal length will be negative. Okay, so this also will be negative actually. So এখন এইটাকে negative, so this is f is equal to, see, f, since this is negative, this is a constant term, the focal length will also be negative if this is going to be positive. Okay, focal length will be negative because this diverging length, it says diverge, parallel rays are diverged. Okay, so focal length has to be negative obviously. So therefore this particular part has to be positive. This must be positive. Okay, this must be positive. Okay, so if that is the case, then if this is the case, so this must be positive. Okay, what does this mean? Mu2 hence the length should be filled with what? Filled with L2 and imagine L1. Okay, so hence this should be, I'm sorry, filled with L2 and imagine so it has to be immersed in medium L1. Okay, so this is the answer. I think Sorry, lens. Yes, lens has to be kept in L2. Right. The answer will be, sorry, the last one. So the question third, let us go to the question third. So in this question, say it is said that a convex lens is in contact with concave lens. Okay, concave lens. Magnitude of the ratio of the focal length is given. Their equivalent focal length is 30 centimeter is also given. So this is the question from combination of lens. See, when we have two thin lenses in contact, okay, thin lenses in contact, and both of them, let me just draw it properly. They have different focal length, f1 and f2. So what will be the focal length of the combination? If I take a single lens equivalent to this combination, then see focal length will be, equivalent focal length will be 1 over f1 plus 1 over f2. Okay, so the equivalent focal length is given already, and the ratio of their focal lengths are given. Let us say, so f1 by f2 is equal to this. So if we say f1 we have find out, then so I can just convert it into a single one, 2 by 3 f2, then okay, this has to be inverted anyway. So let me just go to the next page. Here the ratio is given, so f1 can be written as 2 by 3 f2. If we put it here, pi by 2f, so f2 will be f2, sorry, this is f equivalent. F equivalent is 30 centimeter, I hope. 30 centimeter focal length. So this is about F1. So their individual focal length we have to find out. F2 is found out. Okay, I think there is some issue with this. Let me check. The equivalent is 30. So 1 over 30 means 1 over this 2:1 are the focal length. 2:3, right? 2:3. Actually, this will be okay. Okay, yeah. So one is convex and another one is concave. So that's the reason we had the problem here. So what we have to do, we are taking this F2 as negative. So let us take this as F2 as concave. So we have to take here negative. So you will get eventually minus, that means 1 over 2 F2, sorry, 2 F2, yes, F2. So from here it will be easy to get here. So 1 over, so F equivalent is equal to 2 F2. F equivalent is 30, right? 30 centimeter divided by 2. This is F2. F2 is for concave we have taken. So F2 will be minus 15 centimeter. Okay, this is for concave, and convex we have to find out. Once we get this F1 we had taken at 2 by 3 F2, right? Centimeter. Obviously this F2 is the magnitude of F2, and this will give you 10 centimeters. Okay, this is for convex we have assumed, so it will be positive. So the answer will be D. Now here is another question. This is also a very good question. Let us solve this. A biconvex lens is formed. Biconvex lens is formed with two thin plano convex lenses are shown here. Look, sorry, this is shown here like this. So it is actually a thin lens. Actually, it is made by two planar concave lenses. So this is now actually convex lens. So a biconvex lens is formed by two planar convex lens. So this side will be, see, there are two parts here, right? For this side will be like this, the other side will be like this. So that these two are just in contact and made this. Now refractive index n of the first is given, first lens is given and second lens is also given. So n1 n2 are given. Look here for this particular part, suppose this is n1, see 1, it has n1 1.5 and that of n2 here n2, this is n1, n2 is actually 1.2 centimeter. Both the curved surfaces are the same radius of curvature. Eventually this is okay, anyway this is given. For this biconvex lens, for an object distance 40 centimeter, the image distance will be, so you have got a lens in combination. It is, see, it is actually formed by the combination of these two planar convex lens. So you need to find out what will be the focal length of this particular lens formed by two planar convex lens. So for that we'll be using the formula, lens maker's formula. You know what is that? 1 over f is equal to mu2 minus mu1, mu2 minus mu1 divided by mu1, 1 over r1 minus 1 over r2. So this is the formula, left focus formula. Here we'll be using for both the surfaces. See, in one case, see, this is actually r1, this is r2. So r2 is infinity in this case. For this case, it is r1 is infinity. Okay, r1 is infinity and r2 is this curved surface. Okay. So we need to find out the focal length of each planar convex lens first, and then we have to find out the equivalence of them. So what are the parameters over here? Focal length is 40 centimeters. And object, sorry, this is object distance. I'm sorry, this is object distance. That's why we need to find out what is the focal length. Okay, so here, see, if I just go with this figure, single figure, and write this formula. This is 1.5 minus 1 divided by 1.0. Anyway, this is first term. This here will be minus, but in this case we have to check what are the parameters. See here, this is this side, so R1 will be negative minus 14. So in this, I'm sorry, the other part, we need to actually get for the this part alone. See, R2 is infinity, so this is infinity. 1 over infinity is 0. So what you get? 0.5 by R1, or F is equal to R by R1 by 0.5. Okay, so R1. So from here, F1 will be obtained actually. R1 is 50, anyway this. It will be around 28. Okay, this will be around 28. So one is 28. Similarly, for the other one also, we can find out. So we have got, see what we have got. We have got F1 say 28 centimeter. So similarly, we can find out 1 over F2 is equal to 1.5 minus 1. So this is fixed 1 over infinity minus of my minus of this one. So minus was there, so it will be positive. So this is actually given as 14. Okay, so it will be actually, okay, let us get 1 over f2 itself. Somehow, just let me, okay, refractive index, it is actually 1.2, 1.2 for this. All right, so this will be 0.2. So 2 by 140, so this is centimeter inverse. Okay, let us keep this as 1 over 70 itself. So we will get 1 over, so this equivalent as 1 over 28 plus 1 over 70. Okay, so this would actually give you 140 if you just do the LCM. So this is 5, this is 2. So this will actually give 1 over 20. So equivalent is 1 over 20. Once you get this, then it is actually easier to find out the final image distance, where the object distance is already given. So we have already found out the equivalent focal length of this particular lens. So that is 1 over equivalent is 1 over 20. So this is the focal length of this particular combination. Now we have to find out. So 1 over v is equal to 1 over f minus of 1 over u. And this is plus. Now focal length is actually obtained as positive. So 1 over 20, and this object is placed, it will be negative actually. Okay, so this is 140. So 1 over 40 over here. 1 over 40. That means the image will be also formed at 40. Okay, so the image will form at 40 centimeter, which is given is this one. Okay, now we'll take up one more interesting problem. Let me just write the problem. So the image of an object, formed by a plano-convex lens at a distance (8 meters) behind the lens is real and is one-third of the size of the object. The wavelength of the light inside the lens is so the wavelength of the light inside the lens is 2 by 3 times the wavelength in free space. Wavelength in the free space. The radius of the curved surface of the lens is the radius of the curved surface of the lens. The radius of the curved surface of the lens is 1 meter, 2 meter, this is 3 meter, sorry, 3 meter, 6 centimeter, last option. So how to solve this problem? This is from JEE 2013. It is 13. Okay, so see, in this case, the question we have to understand properly. The image of object formed by a plano convex lens at a distance of 8 meter behind the lens, and it is a real image, and size is also given, that is the 1/3 of the size of the object. Okay, that is what is given. So what all we know? We know the V, we know. Okay, V we know, so that is meter. In meter, everything is meter here now. The size is wavelength inside the, this is actually, this is there. That is what is given. This is, suppose, let us write this as material. Okay, so these are the informations given over here. You have to find out, see, for this, see, this is H prime, right? So that means, you know, M V by U. So this is given 1/3. So from here, actually, you will be able to get this U is actually obtained as 24 meters. Okay. Now What we know, lens formula 1 by f is equal to 1 by v minus 1 by u. Here v is, u is, this will be with the minus sign. Okay, so u will be minus 24. So this is positive 24. So if we just do this simplification, this is 24, 3 plus 4. Sorry, this is 1. This will give, this will give, sorry, this is 6. 4 by this means 6. So focal length is 6. For for plano for plano-convex lens, we know f is equal to r by mu minus 1. For plano-convex lens, because one side will be infinite, so that's why it is true. Okay. So we need to actually find out r is equal to f minus, sorry, mu minus 1 into f. So this is, so for the plano-convex lens, we have obtained this as this. So focal length will be 1 over r. So refractive index was given actually. That was given 3 by 2. So 3 by 2 minus 1. This is into. So this will be actually 3 meter. The question was, option is this one. So the radius of the curved surface of the lens, that is what was asked to find out. With this, I will stop it here for today. Next day we'll learn about refraction through prism and microscope.